Howdy, this is your friendly neighborhood physics teacher here, and we're going to go over Unit 3's FRQ in the College Board classroom. So we're going to do question 1 and then question 2. So question 1 starts. This question is a long free response question. Show your work for each part of the question. And then it goes into a diagram. So you see the ceiling. You have a little motor here with a string connected to a block. And then it gave you your angle, it gave you your length. It's showing you that it was going in a circle, and it gave you your radius. And it's saying that it's going that way. Okay, so in the apparatus shown above, one end of the string of length L is attached to a block of mass M, and the other end is connected to the axle of a motor that rotates, causing the block to move in a circle of radius r at a constant speed vt, such that the string makes an angle theta with the vertical. A student wants to use the apparatus to make measurements to create a graph that can be used to estimate the acceleration g due to gravity at the surface of Earth. The student can adjust the motor to achieve different tangential speeds of the block. So part AI states, the block below represents the object as it travels in the horizontal circle at a constant tangential speed at the position shown in the figure above. On the dot, draw and label the forces, not components, exerted on the object. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So you have a dot. You're just drawing a free body diagram. So hopefully you put force of gravity going down. And then the only other one is your tension force, because you have a string, so therefore you have a tension force. Hello. Okay. I want it a different color. You have your force of tension. And there you go. And that's it. You got 2 points, 1 for each. Woohoo! So A double I. A double I says derive an expression, so expression just means equation, for the block centripetal acceleration c in terms of m, theta, and physical constants as provided. So we're only allowed, so once we get done with our equation, so we're looking for AC, so AC can stay. Our m, our theta, and then our only really physical component would be g. So those are the only ones that can stay. So we're solving for our AC. So let's start with our centripetal force equals mass times AC. What would be our centripetal force? Well, if we go over here and look at our free body diagram, so gravity points down, our force of tension points up and to the left, so that means we can turn this into x and y components. So this would be our force of tension in the x, this would be our force of tension in the y. Our force of tension is the one that's pointing towards the center. So our centripetal force ends up being our force of tension in the x direction, equals mass times AC. Now our force of tension in the x, you would do your sine and cosine. So our theta is up here. So that leaves this as hypotenuse, this is opposite, this is adjacent. So that'd be sine theta equals opposite over hypotenuse. Sine theta, our opposite is our force of tension in the x. Our hypotenuse is just our force of tension. So you get that your force of tension in the x equals force of tension sine theta. You're going to plug that into here. So force of tension sine theta equals our mass AC. Well, we have theta, we have mass, so we're doing good. We need to get rid of our force of tension. So now, and this is all, in theory, in the x direction. So let's look at our net force in the y direction. Equals mass times acceleration. So our y direction has our force of tension in the y and force of gravity. So we'd have our force tension in the y minus force of gravity, because they're going in opposite directions, equals ma. Again, we can break down our force of tension in the y, so that's adjacent. So then that'd be cosine theta is adjacent over hypotenuse. Adjacent is our force of tension in the y, hypotenuse is force of tension. Again, just pulling that over. And so you get your force of tension in the y equals force of tension cosine theta. And we're going to take that and plug it in there. So we get our force of tension cosine theta minus force of gravity equals mass times acceleration. We can break down force of gravity even more. We get mass times acceleration due to gravity equals ma. So now we have our force of tension, just like we did on the other problems. We can substitute in. Let's manipulate this one and plug in. That'll be a little bit harder to manipulate. So we're going to divide both sides by sine theta. And so we get our force of tension equals mass times your centripetal acceleration divided by sine theta. We're going to plug in. Actually, no, because that's going to make centripetal acceleration. You can do it that way. After looking at that, that's going to be a little bit too difficult, because then you have to separate and all that fun stuff. So manipulating, and that's okay if you sit there and be like, nah, it's going to be too hard. So we're going to manipulate this first. So we're going to add our mg to both sides. So we get our force of tension, cosine theta, equals ma plus mg. Now we're going to divide by cosine. And so we get that our force of tension equals ma plus mg over cosine theta. And to show how it's really easy to mess up, I just messed up. I did all this work for no absurd reason. And the reason is because I assumed, or I was thinking that it's moving in the y direction. It's not moving in the y direction. It's only moving in the x because it's circling around here. It's not going in the vertical at all. So I completely messed up here. We still needed this up here. That's not that big of a deal. But our net force in the y is 0 because it's not moving. So since it's 0, that means our force of gravity equals our force of tension in the y. So we can still bring this down here. So we get that our force of gravity, which we can break down into our mass times gravity, equals force of tension cosine theta. There we go. That makes a little bit, because I'm sitting here going, how do I find acceleration? My brain was not having it. So force of tension equals mg over cosine theta. You can take that, plug that into there. So you get mg cosine theta times sine theta equals mac. And then you needed, we're trying to solve for AC. We're trying to get AC by itself. So we're going to go ahead and divide both sides by m. So we get that AC is mg sine theta times cosine theta m. What happens to your m's? Your m's actually ending up canceling, which shouldn't surprise you, because if you remember doing any stuff that we did with centripetal force, our masses always end up canceling. So you end up getting g sine theta over cosine theta equals a. If you remember, if you know anything about trig, you could take it a step further. You don't have to. You don't get a point for doing this, but in theory, this is your g tan theta, because sine theta divided by cosine theta does equal tan. So it's technically but either one of these would be acceptable. So yeah, so pay attention to your forces in the x and forces in the y's. If it's not moving, remember it is balanced and they equal each other. Makes life a whole lot easier. So next part is part B. Using the expression apparatus shown above and the available equipment designed and experimental procedure the students could use to estimate the acceleration g due to gravity to the surface of the Earth. So in the table below, list quantities and associated symbols that would be measured in the experiment, and the experiment used to measure them. Also, list the equipment that would be used to measure the quantities. You do not need to fill in every row. Just use the space you need. If you need more, add more. So to think about, so go back to like your equations. Think about what you need. So we need, so a couple of things. So this would be BI. So quantities to be measured. So we can measure the length of the string. That would be a symbol for L, and you would use a meter stick for that. We need a radius. Definitely need the radius of the circle path. That would be represented with an R, big R, little r, something R, and again, we could use a meter stick for that. And another big thing is we need time, represented with a T, and we can use a stopwatch for that. So if you want to be more specific on time of one rotation. So, and that is just 1 point. So filling out this stuff is just 1 point. So don't fret about it. So to get all of those, you had 1 point. So the double I states, describe an experiment procedure to estimate the acceleration g due to gravity at the surface of the Earth using the apparatus. Give enough detail so that other students could do it. So again, this is you're just making the procedure. And this one's worth 1, 2, 3, 4 points. You got a point for stating a plausible method. So if you came up with an idea, and they were like, yep, that should work. You got some points. You get a point earned for measuring quantities that can be used to determine the tangential speed, so your radius and your time. So that's why you needed those. You get a point for measuring to determine theta and radius. So to need that, you needed your radius and your length. And then you got a point for is earned for attempting to reduce experimental unnecessary. So if you thought of any errors you could have fixed. So an example that they had is the speed of the motor should be set so that the object revolves around in a circular path at a constant tangential speed. A stopwatch can be used to measure the time it takes for the object to make one complete revolution around its circular path. And the meter stick can be used to measure both the radius and the circular path, the radius of the circular path, and the length of the string. The angle can be found by relating the radius of the circular path and the length of the string with the sine of theta. So basically, you turn this into a triangle right here. That's all they did. They got the length here, they got the length here. And so you have hypotenuse, that's your opposite, so that's sine. So they just used your sine opposite over adjacent to find your theta. Alternatively, the angle from the vertical may be measured by filming the experiment using a slow motion camera and using a projector to measure the angle from the vertical in the camera images. So they even took it a step further. They're like, oh, you could record it. The procedure can be repeated for 5 different tangential speeds that cover a wide range as possible using the available equipment. See, and I would almost take it like, so they just said use, the reason you need a variety of different velocities is to make sure gravity is still constant. No matter how fast it's going, gravity still acts the same. So there you go. So C, a student wants to analyze the data collected from the experiment by correcting a linear graph that can be used to estimate the acceleration g due to gravity at the surface of Earth. State the quantities should be plotted on the horizontal axis and what quantities should be plotted on the vertical axis in the linear graph. So again, let's go back to our equation here. So we're going to go back to this mess over here. So you get 1 point for listing the quantities that were either measured or can be determined to be measured. And then 1 point was earned by listing quantities that can be graphed to determine G. So we're looking for G. So if we look at this equation that we came up with over here, so this is C. So G tangent theta equals A. AC. So we're looking at this. But we can't really measure AC. We'd have to break AC down. So remember, AC equals V squared over R. And remember, V, our velocity in this case, is the distance, which would be our circumference, which is 2 pi R over time. And that's squared. So all that squared. Well, not yet. Okay. So if we plug that back in, then it'll be squared. We're going to take this, plug that into there. So we get 2 pi R squared over R. That square goes to everything, so it ends up being 4 pi squared R squared, oh, sorry, divided by T squared. I forgot to divide by T over R. One of your R's gets canceled out, so you get 4 pi squared over r over t squared. That equals your AC. So you take that, plug that in there. So G tangent theta equals 4 pi squared r over t squared. The 4 pi r squared you can actually ignore. Those are constants. They don't affect it. And it's kind of, you have tangent over here, and you have your r over t squared over here. It really doesn't matter which you make what, but you could do your horizontal to equal your r t squared, and your vertical to equal tan theta. There you go. Because it's g, and they're already linear. It's one's on one side, one's on the other. It's already linear. You don't have to do anything fancy to it. So you just put one on one, one on the other. There you go. So C double I states initiate which value of graph could be used to determine G. So we kind of already did that. So indicate which feature of the graph could be used. Oh, so which feature could you use G for? So again, I kind of already started it. We sit here and figured this out. You would realize that the slope of the graph would be G. So you start messing around this with this. So if we continued with this down here, because this is C double I. If we're trying to, so G would end up being, again, if we're ignoring that part, it'd be R over T squared over tan theta. So this would be your rise over run. So you realize it's your slope. So there you go. So that's question 1. So question 2. So question 2 states that this question is a short free response question shown your work for each part. So it gives you 3 different, you have system A, system B, and system C. So system A is a circle. Okay. And it's going like this. R and S. So that's system A. So horrible circles. But 4 and P and radius. System B. 4 MS and P, or like that, R, and that's system C. So 3 different planet-star systems, which are far apart from one another, are shown above. So the middle's a star, is the planet. The masses of the planets are much less than the masses of the stars. In System A, planet A of mass MP orbits star A of mass MS in the circular orbit of radius, and it just goes through the same. So planet B orbits star B, planet C orbits star C. So basically it puts what you see here into words. A. The gravitational force exerted on planet A by star A has a magnitude of force naught. Determine the magnitude of the gravitational forces exerted in the system B and system C. So magnitude, so we're looking for the magnitude. So you get a point for system B, we get a point for system C. So system B, if we're looking at system B, so magnitude of the gravitational force exerted on planet B on star A. So planet B on star A. So this is where we're kind of playing our force of gravity equals our gravitational force, m1, m2 over r squared. So our mass of planet B times mass over r squared. So the only really big difference is the 4. So from our initial will just be times 4. So you're just looking to see what the difference is between this and this original equation, and that's that 4. So let's do it again for this setup. M1, M2 over r squared. So our mass of the planet times our mass of the star over r squared. Again, the only big difference is the 4. So it would be 4. So the answer to them is the exact same. The net force, or the magnitude of the gravitational force from beginning to end is 4 times your initial force. So B states, how do the tangential speed of planet B and planet C compare to that of planet A in a clear, cohesive paragraph-length response that may also consist of equations and or drawings provided? So why the tangential speed of B is either greater than, less than, or equal to planet A, and why is the tangential speed of C greater than, less than? So hopefully you can see that they're both going to be greater than, and it's because of, for system B, it's because the planet is 4 times as much as system A, and then for system C, the star is 4 times as much mass as system. So you got a point for it. So in your paragraph, you get a point for relaying that the net centripetal exerted on the planet from its star and the gravitational, so basically it's saying Newton's third law. So you got a point for stating, it's the same from there to there. You got a point for correctly reasoning or deriving related planet speeds and star masses. You got a point for saying that planet B has the same tangential speed as planet A, and C would be greater than planet A. And it's because, again, you're dealing with the force of the stars is going to be the same here, but this star is stronger. And you can kind of show, so if you wanted to use an equation to show that, you would, do your net force equals mass times acceleration. You're being specific with your centripetal force. And your centripetal force would be your force of gravity. And so you have the end of the planet, the star, divided by your r squared equals mac. You could break down, and this would be of the planet, your mass of the planet. You could break down your AC to be v squared over r. Plug that in. And planet, m star, it's an S, I promise, over r squared equals m v squared over r. You can actually get rid of one of your r's. And then, so you get G, M, P, M, S. Oh, and you can get rid of your mass P also. Hold on. You can get rid of the mass of your planet, because we're just focusing on the stars. So mass of the star divided by r equals v squared. Get rid of the square, you get square root. So v equals the square root of g ms over r. So that basically you're stating that your mass of the planet, velocity, and mass of your star refer to the mass as planet. Yeah, so you're just telling you what the letters, so they just broke down and told them what the letters mean. So the planet's tangential speed is therefore proportional to the square root of the star's mass and independent of the planet's mass. As a result, the tangential speeds are the same for planet A and planet B because the star mass is equal, and greater for planet C because the star mass is greater. And this is just a equation way to kind of step through it, and then you just kind of explain the equation. And the biggest thing is because the way the question is stated, it's saying the tangential speed of planet B and of the planet. So that's why your centripetal force, you would use of the planet here because you're trying to find the centripetal force of the planet. And that's why the masses cancel. So that is part 2 of Unit 3. Remember, you're loved and appreciated. If you have any questions, please ask. Bye.